Okay, so today we're going to talk about lattice enumeration. This is what I did over spring and summer 2015. I was working with Professor Don Davis of High University. So, this work continues a paper he wrote on the same topic. Let's get some basic definitions down, basic notation. As is usual, we write bracket k for the set of integers from 1 to k, and 2 to the bracket k for its power set. Very standard. Now, if M is a set of sets x1 through xk, and S is a subset of bracket k, we write MS equals the union of I element S xi. Very straightforward. We say M is proper if it is never the case that xi is a subset of xj, so there are no redundant sets per se. Any M defines a lattice of M on 2 to the bracket k by S less than or equal to t if MS is a subset of MT. Finally, two such lattices L and L prime are equivalent if there is a permutation sigma of bracket k such that S is less than or equal to t with respect to L, if and only if sigma of S is less than or equal to sigma of t with respect to L prime. This brings us to the following question. How many equivalence classes of LMs are there for M proper and of size k? Now, you may of course be wondering why you would care about this. The answer is because it comes from a problem in algebraic topology that's involved, among other things, Stanley-Reisner rings. If you're actually wondering what this number means outside of the number of lattices, well, it's not exactly clear. By that I mean there isn't a clear algebraic topological construct as counted. Well, at least we haven't been able to find one. Now, for small k, this is very easy to compute by hand. For example, for k equals 1 and 2, there is only one such equivalence class. K equals 1 is trivial, there is only one lattice, and k equals 2, you just flip it around when you perform the permutation and get one class, so that's trivial. K equals 3 is a bit more interesting in that there are 4 such equivalence classes. The proof is again though fairly simple. There are 3 non-trivial inclusions: M1 subset M2 3, M2 subset M1 3, and M3 subset M1 2. The number of these you choose corresponds to the equivalence class. If you're wondering why it makes a difference, or rather why it doesn't make a difference which one you choose, it's because of the permutation. M1 subset M2 3 is under permutation the same as M2 subset M1 3. Now, to get k equals 4, we'll need a bit more information, some more constructs. Because we require M to be proper, we're going to view M slightly differently. Instead of being defined by the inclusions, we're going to view it as being defined by equalities MS equals MT. You can see that this is equivalent, it actually makes a bit more sense to call this a lattice. Now, we write SK to denote the subsets of bracket K of cardinality greater than 1. A configuration of size K is an equivalence relation on SK such that S is equivalent to T implies that for all I element of K, S union I is equivalent to T union I. This property is called unioning. We say that two such configurations are equivalent if there's a permutation sigma of bracket K such that S is equivalent to T if and only if sigma S is equivalent to sigma T in the second relation. Finally, we say that the configuration is realizable if there's an M such that S is equivalent to T if and only if MS equals MT. Now, the main result of the paper Davis wrote before was that there are 50 equivalent classes of configurations of size 4. The way he proved this was to break into cases the number of 3 sets that were equivalent to 1, 2, 3, 4. And yes, we're writing 1, 2, 3, 4 for the set containing 1, 2, 3, and 4. We do the same throughout after this. If 0 of them are equivalent, then there's only one equivalence class. Because of unioning, we can really only have things being equivalent to themselves. If 1 is equivalent to 1, 2, 3, 4, we get the grand total of 4 equivalence classes. 2, we get 14. 3, we get 20. And 4, we get 11, for a nice grand total of 50. Now, I'm not going to go through each one of these cases, but I will show you case 3. Without loss of generality, assume the 3 sets are 1, 2, 3, 1, 2, 4, and 1, 3, 4. Then we may have 0, 1, 2, or 3 of 1, 2, 1, 3, and 1, 4 equivalent to 1, 2, 3, 4. So we'll break into cases again. For case 0, we can have 0, 1, 2, or 3, have 2, 3, 2, 4, and 3, 4, equivalent to 2, 3, 4. For case 1, without loss of generality, assume that 1, 2 is the one equivalent to 1, 2, 3, 4. Then by using it, that limits us to only a few possibilities. We can have 0 or 3 of 2, 3, 2, 4, and 3, 4 equivalent to 2, 3, 4. Or we can just have 2, 3, or just 3, 4, or 2, 3, and 2, 4, or 2, 3, and 3, 4. Case 2 is symmetric to case 1, and case 3 is symmetric to case 0. Thus there are 4 plus 6 plus 6 plus 4, or 20 equivalence classes, in which there are 3 sets equivalent to 1, 2, 3, 4. Now, there is one small detail afterwards to take note of, and that's whether these configurations are realizable. And the answer is yes. All 50 of them are. Now, I'm not going to prove that because the proof is basically For example, the way it was done was, if I recall, Professor Davis wrote a program that went through each equivalence class and constructed a realization. So, it's basically a list of 50 equivalence classes and then 50 sets. Not exactly a fun thing to read through. Now, this does lead to an actual question. How can we extend this to k equals 5 and k equals 6? No, we tried a number of ideas and ultimately settled on trying to generalize the proof for k equals 4. We eventually found that on its own, that proof went as follows. We chose a group of possible equivalences, broke it down into cases based on how many we would include, eliminated any rules that contradicted these choices, or for that matter, any that were immediately implied. We then chose another group of possible equivalences, and so on. That led to the following algorithm. Now, proceeding forward, we're going to call an equivalence between sets of a different size a rule. Note that equivalence is defined by its rules. We're going to partition the possible rules as follows. R1 is going to be rules from k sets to k minus 1 sets. R2 will be rules from k sets to k minus 2 sets, and so on in circles, all the way down to sum Rn, which is rules from 3 sets to 2 sets. This, as I mentioned, triply covers all possible rules, and the number that we're looking for, the number of equivalence classes, is going to be a result of calling a function we defined called num_configs, and the input empty set, and the list R1 through Rn. Now, num_configs is a subroutine we defined, which determines the number of configuration classes given a pre-existing partial set of true rules and false rules, and a partition of all the remaining rules. We're going to count this in the variable n. The first thing that we're going to do is for every element of the partition, we're going to cleanse it, or define that as the next side. Then, for every value from 0 to the size of the first part of the partition, we're going to get a set of sets of true rules from the routine configs true rules, false rules, R1 and R. We're then going to recursively call num_configs on every element that is a set of true rules within this BS, and we're going to add it to the existing n, and then we return n. Now, the cleanse subroutine intuitively removes the redundant rules. First, we go through every rule in R. If true rules implies it, then we're going to add it to true rules and remove it from R. On the other hand, if there is a false rule, which is implied by R, we're going to remove it from R and add it to false rules because it can't be true. Finally, the config subroutine takes a set of true rules, a set of false rules, and a set of rules we haven't determined, and it's going to generate possible partial equivalence classes based on wanting to include I of these undecided rules. So we're going to start by taking an empty set S. Then we're going to generate the list of permutations which fix true rules and false rules. Finally, we're going to tame the I subsets of R. Then for little k and big K, if there is an S in S and a sigma in P such that sigma of K equals S, then we are going to throw it away. If no such thing exists, then it's a new configuration and we're going to add it to S. Now, I want to ask you something. How quickly do you think you could implement this algorithm? It's actually rather surprisingly difficult. This is because of just how slow the algorithm is. Now, I'm not going to actually show you my implementation because it's rather long, rather poorly commented, rather hard to parse, and rather, at the end of it all, boring. Trust me, you don't want to see it. It's also rather, well, simplistic at times. It doesn't perform certain optimizations. Like, for example, it only uses one core. The reason for that is actually because it uses so much memory. If you were to try to run multiple versions at once, it would crash your system. In fact, performance has been the single greatest issue we faced. That brings us to our first lesson. Python is evil. When we began implementing the algorithm, we expected K plus 5 would probably yield 2,000 or so equivalence classes. K plus 6 would maybe be 10,000. Python should be able to handle that, right? The ease of coding should outweigh the performance costs. Well, it couldn't. K plus 5 it was able to do over a very long period of time. K plus 6 it couldn't even begin. So we began to rewrite into C++. And again, we underestimated just how slow this algorithm is. So one thing I used quite a bit in the algorithm was sets. They're fairly ubiquitous. So we then figured it would probably be okay just to use the STL set class to represent them. And the performance slowdown, if we're using something like vector, would probably be worth it for the underlying similarity to the data structure. We were wrong. This brings us to the second lesson. The STD set class is evil. No matter how much of a performance upgrade we got for moving from Python to C++, it was not enough at first. Now, We eventually moved over to better constructs, and again, they were not enough. That brings us to the third lesson. The whole STL is evil. Even using the fastest implementations, many of which weren't even in the traditional uses, basically hacks of hacks of hacks, and it still takes a long time to get K+5 done. K+6 still isn't done. It's been running for over a month. Who knows when it'll finish? Now, you may think, okay, just throw out all this code and rewrite it from the beginning with performance in mind. Squeeze every little bit out of it. Use bit operations if necessary, and so on. This was not possible at the time for one reason. MinGW64 is evil. So, at the time, I was using Windows. My compiler was MinGW64. I needed the 64-bit portion, again, because this algorithm uses so much memory. And by the way, just to give you an idea of how much memory this is using, my current machine has 16 gigabytes of RAM, and it's using routinely anywhere from 90 to 95% of that. But anyway, we were using MinGW64. In my personal experience on Windows, this always tended to be the fastest compiler available to me. Unfortunately, it has some issues. So very routinely, throughout the algorithm, I'll make a local variable, and then I'll instantiate it with something from a function call, which was allocated from the heap. And then I will have to free that variable. If you do this too much, it will crash the program for no inherent reason. By that I mean it is certainly a compiler error. As a result, when I implemented a bunch of memory usage optimizations, the program would simply crash. It would take an allocated variable and somehow turn it into a segfault. So I have no idea why. Maybe it's been fixed by now. I really never want to deal with it again. Now, if you're wondering why I didn't simply move to Linux, it's because at the time I wasn't able to. I since have, and have made it further in the computation, even without optimizations, than I ever did on Windows. Now, this has got me two results. For K+5, we got 7,443 equivalent classes of configurations. K+6, we know that it's over 2,506,113. That is the first 4 sub-cases. It is still in progress, and who knows again when it'll be finished. Now, that's obviously the first thing we need to do, is let K+6 finish. Maybe that'll happen within the next 50,000 years. Now, The next thing we have to do after that is try that and optimize it. If we can get table 6 to take less than a month, that would be wonderful. If we could get it down to a week, even better. From then, we need to look at table 7, which we haven't even touched. The algorithm should work for it, but again, it'll be rather slow, given how rapidly the number of configurations is increasing. We can't even estimate what it is. Finally, we need to prove that these configurations are realizable. We still haven't done it, but we have a lot of reason to believe that it can be done. So, that is a summary of the work. Are there any questions?